Hi, AP Chem students. This is the class video for Monday, January 4th, 2021. Happy New Year. So just a reminder, Unit 4 quest corrections are going to be due Wednesday, January 13th. If you got less than a C, then you need to make an appointment to come see me about this. The optional research proposal is due January 19th. And then for your copper mine, probably ready to get rid of it, what you can do is just put the whole test tube into a plastic bag, seal it up, and throw it into the trash. Homework for tonight is to read the textbook pages or watch the videos on the schedule and take notes. This is also posted in Google Classroom. And then you should do these 5 textbook problems, and they'll be checked for 10 points. The answers are posted with the homework right now. There will be a short homework quiz tomorrow, 10-point quiz based on the practice problems of today's class video, the class, and the homework problems right here. So a brief overview of what's kind of coming and where we've been. So we've finished units 1 through 4 so far, and you can see that units 1 through 4 are a mishmash of different chapters in the textbook. Starting with unit 5, this is kind of the start of second semester chemistry right here. This is like first semester. Bottom here is second semester general chemistry, and except for this thermochem part, which usually is done first semester. And so we will be starting to use the textbook a lot more since we're going to be going by the textbook chapters mostly, and they're not as mixed in like the units before. So we're starting unit 5, which is chapter 14, and it is called chemical kinetics. So basically, kinetics is about how fast a reaction goes. And here are some things that can go pretty fast: a road runner, traffic on a highway, and molecules. In fact, molecules go the fastest of all of these, especially gas molecules. So now we're going to go deeper into reactions. We've finished the fundamentals, and now we are going to look at some details of chemical reactions. And kinetics is all about figuring out how fast the rate of these reactions are, and looking at the details of the collisions to get a sense of how these speeds come about. And so we want to be able to figure out the rates of reactions, how fast reactions go, and be able to manipulate them to go faster or slower. So we study the rate. Kinetics is always relating to the rate of chemical reactions. Chemical reactions have different rates, different speeds, depending on how the reaction occurs and what things are involved. It also is the study of how the reaction actually occurs, the steps. Okay. When we talk about the mechanism, we will talk about the steps, the exact steps, or the process. Most reactions do not happen in one step, as shown in the balanced reaction. There's a numerous number of steps, a pathway that the reaction takes. So we'll study that as well. And there are many daily applications like food spoilage. In class, somebody mentioned digestion, respiration, right? The rate at which you use up your glucose, your sugars, your food is governed by kinetics. Other things like the fading of colors. This is something that, right, people would like to preserve the color, a pigment in a paint or clothing for as long as possible, and to kind of let that slow down is a part of kinetics, right? Same with food spoilage. You don't want the food to spoil, so you're trying to slow down a reaction, whereas there are some reactions where we want to speed them up, like this reaction here. of nitrogen plus hydrogen to make ammonia. This is the Haber-Bosch process. And without a catalyst, which is something we'll talk about very soon, this reaction goes very, very slowly. So we want to be able to speed up this reaction, whereas there are other reactions like food spoilage that we want to slow down. And all of this is about kinetics, the rate. So again, here, right, we're going to study the rate. We're going to figure out what factors, what affects the rate, and how much. Then we are going to be able to figure out what the mechanism is, how the reaction occurs. And then at the very particle level, the nanoscale level, we are going to think about the frequency of collisions between the reactants. The reaction can only happen if the reactants collide, right? The reactants must touch and collide in order to get a reaction to occur. However, we're going to learn about this later. Not all collisions are actually going to produce products, right? Because they need these two things. They need enough energy and they need the correct orientation. We'll talk about both of these things very soon, but basically these collisions need to get over this energy barrier in order to get the products. And the higher this energy barrier or this activation energy is, the harder and harder it is for collisions to be productive and make the products. That makes the reaction slower as this activation energy gets higher and higher. So here are the factors that affect reaction rates. So first of all, surface area and physical state of the reactants. In order for things to react, again, the molecules have to collide. And the more homogeneous, the more mixed the reactants can be, and the more surface area that the reactants present, the faster the molecules can actually react with each other. So if you think about the three states of matter, solid, liquid, or gas, which particles collide more? Think about it. Okay, gas particles collide the most. They are the fastest moving. They mix completely with each other. Okay, and they are very dispersed. And so they take up their whole volume as well. They take up whole volume and spread out. So there are many reasons why gases will react much more quickly than solids or liquids will react. So here are a couple of demonstrations that the lycopodium powder, actually, lycopodium is a pollen from a conifer tree. I don't remember which one. This is a demonstration that I like to do to show how surface area affects the rate of combustion of this pollen. So let me show you those demonstrations. And then the second video shows an explosion. So our first video here is Steve Spangler, personal hero of mine. And he's going to show, he's going to put on here on the plate some lycopodium right there. And he tries to light that powder. So even though he's trying to light this powder on fire, nothing happens because, well, the powder is kind of all clumped together. Not much of the surface is being presented to the flame. Now watch what happens when he shoots it into the air over the flame instead.
So you get something that kind of looks like this. Amazing fire. Special effects artists like it because it can't jump back into the container and then cause this to explode. It has to be distributed in the air to give you that good.
So you can see when he sprays the pollen into the air, it's presenting a much bigger surface area. The pollen that gets spread out in the air can can come in contact and with that flame, and then the fireball spreads to the other dust particles around it. So this is very dangerous also in grain elevators. So if you take a look at this grain elevator right here, um, I don't know where this is, but here, grain, flour, or any sort of ground up grain, the dust from that gets dispersed in the air, and if there is a spark, this can happen. So you can see if it happens inside an enclosed building, you can get an explosion as the fireball explodes inside, builds up pressure, and then causes the elevator to break open. So that is the surface area and state of matter, um, the factor that affects the reaction rate. So the more surface area, the more gaseous, okay, and more homogeneously mixed these reactants are, the faster they will react. The next factor is the concentration of the reactants. So as we have more concentration of the reactants, and notice I included pressure, right? Pressure is a form of concentration of stuff, right? Molecules in a volume. So here we have steel wool in 20% O2. That's just air. You can see that we can get it to glow red hot, but if we put the steel wool into 100% oxygen, basically it just catches on fire and turns into rust immediately. So the higher the concentration, we just have more molecules colliding together, and that means more collisions are successful at producing the products. And so we get a rapid reaction as the concentration increases. And we'll see that in this elephant toothpaste video, also another one of Steve Spangler's. So here he's showing 4 different concentrations of hydrogen peroxide. Think about which of these is going to have the fastest reaction. Right now, the reaction is happening, but it is very, very slow. They're going to add something called a catalyst, potassium iodide, to make this reaction speed up. And we'll see the effect of changing the concentration, of increasing the concentration. So here we go. So clearly the reaction is fastest with the highest concentration. Just have more molecules colliding with the catalyst and breaking down into water and oxygen gas. That's the bubbles coming out. Now notice here, nothing's happening before the catalyst is added. The reaction is happening. It's just too slow for us to see with our eyes macroscopically in the real world. So we need a catalyst to allow for the reaction to happen at a quick enough rate that we can actually see this visibly. Okay, so that is our concentration. I love that demonstration, and usually I do it in school. It's just so much fun. All right, the next factor that affects reaction rates is temperature. So at higher temperatures, the molecules are going to have more kinetic energy. They will move faster. They will collide more often with greater energy. And so here's a demonstration with glow sticks. Glow sticks are really fun. And they've placed the glow sticks after snapping them into 3 different beakers of water, and the water is at different temperatures. Which beaker has the water with the highest temperature? So think about our factor and how temperature affects the rate. So hopefully you're thinking, wow, the water on this leftmost beaker must be the hottest because the glow from the glow stick from the chemical reaction is the greatest. So yes, this leftmost has the hottest water. The rightmost beaker has the coldest water. You can see the reaction is proceeding much more slowly, so not as much light is being given off. So temperature is another way we can speed up our reaction rate. Our next factor is the catalyst. So again, here going back to the elephant's toothpaste, right? We can see the reaction now once the catalyst is added. But before the catalyst is added, the reaction is still happening, but it's just happening too slowly for us to see in the real world with our eyes, right? Macroscopically, we can't see any change, even though the change is happening very slowly. It's only after we add this catalyst, the potassium iodide, that the change happens quickly enough, right? It speeds up the rate of the reaction quickly enough that we can see the bubbles forming and we can see the foam. And now the reaction is fast enough that it produces enough oxygen gas and water to make it visible to us. So a catalyst speeds up a reaction, but it is not consumed. Okay, so during the course of the reaction, the catalyst will regenerate and will redo its magic. Basically, it will change the way the reaction proceeds in order to make the reaction go faster. And so we will talk a little bit more about catalysts at the end of this chapter, but catalysts are not consumed. Now, it is not true that catalysts uh, don't have to be regenerated. It is often the case that eventually catalysts, uh, break down, or they can get trapped in other places, or they can get transformed into other things. Right? They're not always as stable as we would hope, but for the most part, catalysts are regenerated and reused during the course of the reaction. One catalyst that we use all the time in our bodies are enzymes. So an enzyme is a catalyst for a reaction going on in our body. So here, the enzyme binds to the substrate. You may have seen this in biology, and it forms this enzyme substrate complex, which allows the reactants to transform more quickly, and then the products leave the enzyme, and the enzyme is regenerated to bind with another substrate molecule and helping to convert that into the products. So we use many enzymes in our body. I'm lactose intolerant, so one enzyme that my body does not produce is lactase. It is the enzyme that converts lactose. It breaks down lactose, which is the sugar in milk, one of the sugars in milk. And so I need to take Lactaid from the pharmacy. Lactaid is a pill that contains lactase, and that allows my body to break down the lactose. So that's an enzyme that is commonly used and available over the counter. Okay, so this next thing is just to help you think about the molecular nature of reactions, right? So here we have OH minus plus this chloromethane and CH3Cl. And you can see here the two reactants, the oxygen needs to bind to the carbon, and this carbon Cl bond needs to break. And as the reactants get closer to each other, bonds are broken and formed as it gets over this most energetic area where the bonds are most strained or most stressed. and return to a point that is lower in energy as the products are formed. So we have attractions that break and attractions that form. And in order for these bonds to break and form, there has to be a collision. So looking at this, just this video quickly, I didn't have time to show it in class. I thought it didn't add as much as that one animation, but you can see that things need to collide in order to transform. I don't know if you just saw that, but that just changed here. And so if the molecule does not collide in the correct manner, it doesn't happen. So just like over here, if the oxygen hit a hydrogen instead, or the chlorine side, it would not happen. It has to have the correct orientation. It also needs enough energy to get over this barrier. Okay, so you need enough energy and you need the correct orientation. But first of all, you need a collision. Okay, you have to have collision. And some of those collisions will have enough energy and will be oriented correctly to give the product. Okay, so we talked about these 4 different factors and we looked at the videos. So here's a kinetics question. So slow rates of chemical reaction are associated with the following. Well, let's think about whether these things would make a reaction slow or fast. Presence of a catalyst. Well, catalysts will speed up things. So that is not the answer. Excuse me. High temperature. The higher the temperature, the more things will collide. The more they will have energy to get over that barrier. So no, this will speed up the reaction. High concentration, again, speeds up the reaction. Strong bonds in reactant molecules? Well, think about it. If these bonds are very strong, they don't like to break and change into products. So this is the correct answer, D. Low activation energy, if we have a reaction that looks like this with this much activation energy, this is called the activation barrier or activation energy, and we have a reaction that has only a tiny little barrier, guess what? Low activation energy means that will be fast. This will be slower than the other. Okay, so low activation energy makes a reaction faster, okay, or lower activation energy. This question will come back to. I forgot that. I put that in the wrong place. All right, so the speed or rate of a car moving, when we think about the units, are miles per hour, or if you're in Canada or some other metric system nation, right, kilometers per hour would be what your car would show. So we're always going to have something per time, right? Rates are given as something changing per time, okay? And we're going to see what that something is for chemical reactions. So here is a representation of a reaction happening. So the reaction that's happening here is A transforming into B. Very simple reaction. And you can see that time is going on. So we're now going to talk about reaction rates with a chemical reaction such as this. So the rate of a chemical reaction is the change in the concentration of the reactant. So we are going to use the change in the concentration per unit time, or the products per unit time. So here's this reaction. A goes to B, and all of these are 1 liter in volume. We're going to have 2 ways of measuring the rate. The speed at which the reactants, okay, in this case A, disappear is called the rate of, very fancy here, rate of disappearance. The speed at which the products appear, again, very fancy here, is called the rate of appearance. Okay, so those are the technical terms. So the way we represent this with our symbols is the rate of appearance of B. B is a product, is a change in the concentration of B, that delta B over delta T, T representing time. The rate of disappearance of A. Now, since A is disappearing, we are going to put a minus sign in front, and it will be the delta concentration of A over delta T. So the most common units are molarity per second, okay, because we use concentration. But just be careful, the rate could be given in molarity per hour, okay? We should always look at the units. It could be molarity per millisecond, okay? Milliseconds, or perhaps they could use millimolar, okay? So millimolar per second. So always look at the units and see what they've decided to give to you. So the symbol delta is this triangle. It's read as change in, and it's always equal to the final, okay, value, or the final concentration or final rate, whatever we're looking at, final time, minus the initial value. Okay, so it's always the final minus the initial. And just recall, molarity is moles per liter. Occasionally, people will put the rate molarity per second. They could use moles per liter per second. Okay. Sometimes they will use moles per liter and use that instead of the big M for molarity. All right, so to get an average rate, we're going to take the change in the concentration and divide it by the change in time. Now, the average rate is not going to be used as much. It's not as useful as something called the instantaneous rate, which we'll see on the next slide. The average rate is going to be an average of the rates over two different points in time. So here, we'll just do one of these. The average rate of disappearance of B, rate of appearance of B will be delta concentration of B over delta T. And we're going to calculate the average rate, should have average here, from 0 to 20 seconds. So here, if we look at delta B, remember it's final minus initial. Okay, so final for B is 0.46 molarity, okay, molar. Remember, this is in 1 liter, so if we divide by 1 liter, it'll still be the same number, minus the initial molarity, okay, of B, which is 0 molar. Then we take our T final, our final time, 20 seconds, right? That's our T final. Here's our T initial. So we take our T final, 20 seconds minus 0 seconds. So that's 0.46 divided by 20. Okay, and then we divide that out, and we get 0.023 molarity per second. Okay, so that's our average rate of appearance between those 2 points in time. However, that is not as useful, okay, as knowing, and we're gonna skip these because we're not going to use the average rate very often at all, because it's not as useful as actually plotting this and finding an instantaneous rate. So again, here the average rate is the change over 2 points in time. Okay, so here again, it's a change in this concentration over some time period. One thing to note is that as you start off with this rate at time equals 0, you can see that the rate is decreasing. Okay, so as time goes on, the rate decreases. It's getting slower and slower. It's going down and down and down, because as the reaction proceeds, right, less and less reactant molecules are present, because some of them change into products, and so we have a lower and lower concentration, and that leads to fewer collisions, fewer molecules which collide, and therefore the rate goes down over time. So here is when we plot the concentration versus time, we can obtain a graph of what the rate is doing. And so if we can find the rate at a moment in time, if we want to find the rate at any moment in time, what we can do is make a tangent line to that particular point and then find the slope of the tangent line. Okay, so we can take a tangent line and find the slope of that tangent line to find the instantaneous rate at that particular point in time. The beginning initial rate is called the instantaneous rate at time equals 0, is an important rate called the initial rate. Okay, at the very beginning of the reaction. Those are measured often in order to determine rate laws. So that is a particular point that we want to take note of. This is, as this slide shows, the initial rate is the easiest one to find because the rate slows down over time, so it's the easiest to detect at the beginning. All right, so we're not going to be drawing many tangent lines, but just to show you how this is done, here's the tangent line drawn here to this point at time equals 0. So in order to find the initial rate, we draw this tangent line, and then there's a triangle here in order to find the slope of this line. Remember, slope is equal to rise over run, and that would be delta y over delta x. And so we can take the rise over run of this tangent line to find the rate of disappearance of C4H9Cl. So that's what we're trying to find. C4H9Cl over delta T. And when we look here, the rise is starting with the final 0.060 minus 0.1. Okay, over delta T, it's about 200 seconds, so 200 seconds, and let me put in my units here. This should be molarity. This should be molarity, minus 0 seconds. And so when we divide this out, we get 0.0002 molarity per second. I will try not to make all the math errors that I did today in class. So we could do that for this point as well, since there's another tangent line. However, you will not be asked to graph a tangent line and find the slope of it. But I think it's important to know how this works. In actual calculus, you would have the function of this line and take the derivative to be able to find the slope at any point in time. We're not going to do a lot of calculus in this unit, or very little. Most of it is going to be handed it to you, so no worries if you're, calculus is not your strong suit, because algebra is what you really need to know how to do. Okay, so here this reaction, if you look at all of these coefficients, they're all 1. 1, 1, 1. Okay, so the rate of 1 disappearing is going to be the rate of the product appearing. Okay, so here the rate of disappearance of C4H9Cl is the same as the rate of appearance of C4H9OH. So these rates are equal to each other. But what if these coefficients are not all 1? Like in this reaction, here the coefficients are 2 to 4 to 1. Right, there's a 1 there. Now we've got to relate these rates, and they're going to be affected by the stoichiometry, by the coefficients in the balanced reaction. So for every 1 mole of O2 that's appearing, right, you're going to get 4 times as many moles of NO2 appearing. Okay, right? 1 mole of O2 appears, but 4 times as many NO2s appear at the same time. And in the meantime, 2 times as many moles of N2O5 will be disappearing as moles of O2 forming. So right now the stoichiometry is not 1-to-1. We can't just say the rate of one is the same as the rate of the other. So to relate these rates, we divide by the coefficients of the balanced reaction. So the way we relate these rates to each other are by taking 1 over the coefficient and putting that as a fraction in front of the rate. And that will let us equalize the rates to each other, to relate the rates to each other. And in general, right, here, if these are the coefficients here for a general reaction, right, again, the rates are going to be 1 over the coefficient times the rate, 1 over the coefficient times the rate, and so on. All right, so in this sample exercise, it says, how is the rate at which ozone disappears related to the rate at which oxygen appears in this reaction? So basically, they're asking, how are these rates related? Can you write something like this for the stuff that is in this balanced reaction? So yeah, we can. We can put, right, minus 1 over half of delta O3 over delta T. Okay, that's our rate of disappearance of ozone times a half from the coefficient. That's going to be equal to 1/3 of delta O2 over delta T. Okay, so just using the coefficients to relate these rates to each other. So then in part B, it says, if the rate at which O2 appears, delta O2 over delta T, is 6 times 10 to the minus 5th molarity per second at a particular instant, at what rate is O3 disappearing at the same time? Basically, what is this? So if we look at this equation that we just wrote, right, I see that minus the rate of O3 disappearing is right here. We just need to move the 2 over. So what I can do is let me just rewrite that first part. So the thing that we need to find is our rate of disappearance of O3. We need to find this. So if I multiply this side by 2, and I multiply this side by 2, this will be 2/3 of that. So I can do 2/3 times this rate right here, the rate of oxygen appearing, minus 5th molarity per second, and 2/3 of that will be 4.0 times 10 to the minus 5th molarity per second. And so that is the rate of O3 disappearing at this point in time. Okay, here's another practice exercise. In this one, they're asking, what is the rate of appearance of NO2 given this equation, and given the rate of decomposition of N2O5, now we see that that's a reactant. That's just another way to say it's the rate of disappearance. The rate of decomposition is the rate of disappearance. So I want to relate this to my NO2 in here. So let me again write that relationship between the rates of disappearance and appearance while taking the stoichiometry into account. So I can write this down. Quarter NO2. Okay. And now what I want to find is my rate of appearance of this. That would be this. Okay. So if I multiply both sides by 4, I can isolate that, and I will have minus 2 times delta N2O5 over delta T, and that will equal my delta NO2 over delta T. So if I plug this in, I'll get minus 2. And remember, that actually is the rate right here, so we don't need a minus sign anymore. And it's 2 times 4.2 times 10 to the minus 7 molarity per second. And so our delta NO2 over delta T will equal 8.4 times 10 to the minus 7 molarity per second. And the same thing can be done for the O2 concentration and, the O2 rate of appearance. So here now we can see that the 1/2 times the rate of N2O5 disappearing is related directly to the rate of O2 gas appearing. So now we can just plug in for right here for my N2O4 rate right there, 1/2 times 4.2 times 10 to the minus 7 molarity per second. Okay, because that's what that equals. And that will give us 2.1 times 10 to the minus 7 molarity per second for the rate of O2 appearing. Okay, so those are our rates and how we relate them to each other. So now how do we actually figure out how the concentration affects the rate? So we'd like to know how, if we change the concentration to a reactant, how this will change the rate of the reaction. We'd like to know the relationship between these. So something called a rate law is what we're going to write down in order to relate concentrations to rates. Here's a rate law. Okay, so this thing right here, this is a general rate law. This is called the rate law. It's always of the form rate, starts out with rate, equals, and then K times the concentrations of the reactants raised to some power. Okay, raised to with some exponent. A and B are the reactants. The exponents M and N are called reaction orders, or order of reactants. Reactant orders. This proportionality constant K is called the rate constant. The overall reaction order is the sum of the reaction orders. So the overall reaction, order of reaction, is m plus n and so on if we have more exponents, more reactants. So we'll take a look at an example to see how these reactant orders are related to the rates. Okay, so what we want to do is here we have a chemical reaction. We want to figure out how does the rate change with this concentration of NH4. We want to figure out how the rate changes when we change NH4. And to do that, we want to find a place where NH4 plus is changing, but the other reactant, NO2 minus, is not, right? We want to take that out of consideration. So if we look here, experiments 1 and 2 are where NH4 changes, but NO2 is constant. Okay, NO2 minus constant. Okay, but NH4 changes. So looking at experiments 1 and 2, which were the ones we picked, we can see that when this concentration doubles, okay, so times 2, this rate also doubles. It goes up by 2. Now, what if you can't see that? Well, you do want to show this, right? You want to show that this doubling happens, and the way we can use some math, right? So if we say, let's see what happens to the NH4 plus in the second experiment, and see how many more times concentration is changing. If we take the second over the first, and I always put the larger number first, right? I just want to deal with, I'd rather deal with larger numbers than decimals. I put in 0.200 molar over 0.100 molar. I divide this out. Well, that is 2, right? It has doubled. If we look at the rate, I can do the same thing. I can put the rate of 2 over the rate of 1, and 10.8 times 10 to the minus 7 molarity per second over 5.4 times 10 to the minus 7 molarity per second. Again, divide this out. This is also 2, right? So we can see that when this doubles, the rate doubles. It's done the same thing. So now let's figure out how the rate changes with NO2 minus. So here we've got to pick 2 experiments where NO2 changes, but NH4 is constant. So if we take a look here, there are actually 2 places where we can do this. We could look at experiments 4 and 5, or experiments 5 and 6. So we could look at experiments 4, 5, or experiments 5 and 6. Both of those will work perfectly well. So we're going to actually use 5 and 6 here. So again, here, this concentration is doubling. So let's just show that explicitly in case you are not able to see that. So NO2 from experiment 6, we put that over the 0.0808 molar over 0.0404 molar. That's equal to 2. All right, let's look at the rates. So the rate of 6 over the rate of 5. If I look at that, that's 43.3 times 10 to the minus 7 over 21.6 times 10 to the minus 7. That's roughly 2 again. So again, here, NO2 concentration doubles, the rate also doubles. And again, this is the initial rate, the observed initial rate. So we see that the rate is proportional to the NH4 plus concentration. The rate is directly proportional to the NO2 minus concentration. So the rate is proportional to these 2 things. And when we write this as an equation, we have to put in this proportionality constant K, the rate constant, to make this an equality, and this is the rate law. And K is called the rate constant. K will be constant at constant temperature. So this rate law shows the relationship now between the reaction rate and the concentration of the reactants. The exponents are going to tell the order. So here, right, the exponent of that is 1, the exponent of this is 1. The reaction is called first order in NH4 plus because the exponent is 1, and first order in NO2 minus. These reaction orders, this is really important. These reaction orders can only be determined through experiments, through experimental data. That is the only way we can confirm the reaction orders. This overall reaction order, we can add up the two reactant orders here, 1 plus 1. Okay, so 1 plus 1 equals 2. So the reaction is second order overall. All right, so in part A here, in the sample exercise, it asks what is the overall reaction order for the reactions described in equations in these two equations. Okay, so in part A, the overall reaction order, looking at the rate law here, it is first order, right? We only look at the rate law to find the overall reaction order. The second one, okay, so it's first order for 14.9. And for the second one, here's a exponent of 1. 1 plus a half. It's going to be 3/2 order for 14.10. Okay, so now we're not going to see, you're not going to find orders that are other than 0, 1, or 2. But in real life, there are half orders, there are 3/2 orders. That does exist. It's just that for the AP exam, they choose nice neat orders like 0, 1, and 2. Here, okay, now in part B, they're asking for the units of the rate constant. So if we take a look here in the first one, rate equals K N2O5. And the easiest way to find the units of this is to put in the units of these other things and cancel out units. So the rate is always going to be molarity per second. K is K, and this concentration is in molarity. So if I solve for K, right, I can put molarity on both sides here. That cancels out. The units for K for this first one are going to be 1/seconds. For the second one, for 14.10, again, let's rewrite that. Rate equals K CHCl3 Cl2 to the 1/2. Okay. Again, let's put in the units for these. Rate is molarity per second times K. This is molarity times molarity to the 1/2. Okay, so then to get K by itself, I need to divide by these things. Okay. Molarity to the 1/2. That's going to cancel out. These cancel out. So K now has a unit of 1/molarity to the 1/2 times seconds. Okay, so there's our units for K for equation 14.10. Oh, actually, they just asked for 14.9, but that's okay. All right, so how do reactant orders affect the rate? So if a reactant is 0 order, okay, that means whatever you change the concentration to, however you change the concentration, there will be no effect on the rate. The rate will not change. So let's say you increase the concentration 2 times. Well, guess what? No change. You increase the concentration 10 times. No change. The reaction just does not relate to the concentration of the reactant at all. It is not affected by how much of the reactant is present. You'll have the same rate no matter what. Here, this next one, a reactant is first order if changing the concentration causes the same change to the rate. It's directly proportional. So if you increase concentration 2 times, you will get a 2 times increase in the rate. If you increase it 3 times, it'll be 3 times the rate. 6 times, 6 times the rate, right? Whatever change you make to the concentration, you will see that same change in the rate. If a reactant is second order and you change the concentration, let's say you change the concentration and you double it 2 times. Now the rate will increase by the square of this change in concentration. The rate will go up 4 times, which is 2 squared. Okay, so this change in concentration gets squared. What if you change it 3 times? Now the rate will be 3 to the second times greater. 9 times, okay, an increase in rate. If you increase the concentration 3 times. 4 times, the rate goes up 16 times. 4 squared is 16. And like I said, 0, first, and second are the ones, those are the orders you will see on the AP exam. Third order, this would be changing the concentration, which leads to a cubic increase of the rate. So if you change the concentration, let's just use 2. If you double the concentration, 2 times the concentration, you're going to get 2 to the third 8 times the rate. Okay, the rate will increase 8 times. That's very rare. Third order and beyond is an extremely rare case. As I mentioned on the AP exam, the orders are always going to be 0, first, or second. But that's not to say that weird orders don't exist. They do exist in real life. So what we need to be able to do is to relate the changes in concentration and the order to the rate changes and be able to recognize those. And note, the rate constant is constant at constant temperature. It does not change depending on the concentration. It's always constant as long as the temperature stays constant.